All right, so we're recording. So as you guys know, today is my last class with you. I told you that Mr. Bussman was gonna take over, not Bussman, oh my goodness. Mr. Bumbalski was gonna take over. That probably made you guys scared for a minute, not Mr. Bussman. I told you guys Mr. Bumbalski was taking over, but he is not, just due to some changes that are happening temporarily. So Coach Fogarty is gonna take over the honors pre-calculus classes for the remainder of the year. So I'm just gonna let him chat with you guys for a minute here.
All right, so we're all excited. Miss Delma's gonna have her baby with her husband and start her new family. It's gonna be awesome. So I'm just gonna jump in there and do the best I can. I won't be as good as Miss Delmage, but I'll try my best. But she's given me all the stuff that she wants me to cover with you guys. And she says you're a pretty good class. So I shouldn't have to do any teaching, right, Kobe? All righty. I'm going to silence myself and just sit back, all right? All the best.
Cool, so he is, Coach Fogarty is gonna continue on with the calculus prep. I gave about 3 weeks worth of stuff to him and then whatever he deems necessary for you guys. My ultimate goal is to have you prepared the best you can be for AP Calc AB next year. So that's the goal. Again, I'm really not talking to any of you guys right now, but I'm just saying this to all my students. Whatever I have assigned so far during this virtual learning fourth quarter, you know, Coach Fogarty is not going to have any part of that. So whatever I've assigned, if you need to make up anything that needs to be sent to me by Friday at noon, so I can get the grades in since Friday's my last day. I'll still be on Zoom office hours today and tomorrow, 2 to 2:30 also. You guys do have an assignment that's due tomorrow by 3:15. Today we are going to go over the same stuff, and I'm assuming we need to go over it some more because it's a new idea. So that's what we're going to do today. So we have been practicing, well, sort of been. We've done 2 examples of the limit definition of a derivative. Charlie, what's up, bud?
Hi, Mr. Mash. I was just wondering, for when we're logging into class, are we going to log in with Coach Fogarty's Zoom ID or with yours from now on? Well, after
Great question.
Friday.
Great question. I forgot to talk about that. Thank you.
Yeah, Ms. Delmage, I have that down here. We're going to send them the link for my video. And we'll do it the same way we did with the geometry guys that I'm teaching, Charlie. All right?
Okay.
So you'll get the link, all right?
Sounds good.
All right, baby.
Awesome. Thank you.
Yeah, Coach Fogarty will send out an email by the end of the week to all of you. It's still going to be the same class time and everything. You're just going to join using his Zoom link, and then he'll upload the classes to his YouTube channel. So, okay. Limit definition of a derivative. So we learned the other day that for any function, well, any function that has a derivative, we're not going to worry about that this year, but any differentiable function f of x, to find its derivative, which is marked with what looks like in English an apostrophe, in math we call this prime. So this is read as f prime. That's how you read it in English. So f prime of x refers to the function's derivative. Derivative is a glorified slope. It's the slope at exactly 1 instant on a function. So we saw that with a line, the slope was, or the derivative never changed, right? A line has a constant slope. That's what makes it a line. Anything that has a greater exponent than a line, like a quadratic, a cubic, quartic, and so on, those are going to have derivatives that change depending on where you are on the function. So f prime is going to give us the equation for what the derivative is anywhere. So we find it with a limit. The limit as h approaches 0 of a fraction. And remember, we got this fraction by using the slope formula, right? Y minus y over x minus x. So f of x plus h. I'm going to color code this for when we do an example here. So we'll do this part in red. F of x plus h minus f of x all over h. Hey, Charlie, are you able to like undo the raise of the hand? I can't, it's like down at the bottom of my screen and I can't choose colors. If you're able to do that. Thank
Yeah.
you.
Oh, yeah.
Thanks. No, it's fine. All right, so we have the limit definition of the derivative written out there. Okay. So this is not the only way to find the derivative. In fact, there are simpler rules that you'll find out, but this is the definition of it. So it's kind of like where it comes from. Okay, so our examples today are going to be just to find f prime. So this is the directions today. Find f prime. Okay. So we're going to first do f prime of a linear function, the easy one. So let's say we have f of x, will be example 1 here. We'll have f of x equals negative 5x minus 2. Okay, so this is just a line, right? It's a linear function. What's the slope of this line, guys?
-5.
-5, awesome. Okay, so it is a negative slope. So since it's a line, its slope is always -5, no matter where we're at, right? That's what makes it a line. So we should end up getting out -5 at the end. That's good to just know. So we're basically gonna do a lot of glorified algebra to get -5 at the end. All right, so let's start. So in order to find f prime equals the limit as h goes to 0 of this big old fraction. So that's what I can write right now, no work. This first part here I'm going to do in red. I'm going to find f of x plus h. Again, this is a lot of notation, but don't let it overwhelm you. Take it one step at a time, right? The first thing we're going to do is plug in x plus h into our function. Okay, that means I'm plugging in x plus h here. I'm plugging in x plus h. I need parentheses and more than one thing. So I'm going to have -5, and then in parentheses we'll have x plus h, and then -2. And guys, if you have any questions while we're going through this, just shout them out. It's fine. Okay, so we plugged in x plus h here. Cool, that was the red part. Then minus f of x. Well, what is f of x? It is -5x minus 2. No work required there, it's already given to us. Since we're subtracting it, we need parentheses. And I specifically picked a problem with a lot of minus signs because we need the practice, right, of distribution. Okay, so let's clean it up a little bit. We still have the limit as h goes to 0. And if you plugged in 0 for h right now, you would end up getting, it would be messy, but you'd get 0 up top and 0 down below. That means we need to just keep cleaning up. So we'll clean up by multiplying the -5 through. And then second, we're going to distribute the negative through over here, and that's going to change both of these terms to a positive when we do that. So we'll get plus 5x plus 2, and then all over h. Okay. Now from this point, when you use this limit definition of a derivative, everything that doesn't have an h in it's going to go away. If it doesn't go away, that means you did it wrong. All right, so the stuff that's going to cancel is the -5x and the +5x, and then the -2 and the +2. All right, so we're left with the limit as h goes to 0 of -5h over h. Again, if we direct substitute in 0 for h, we're going to get 0 over 0. But we can see that the h's will just cancel. We don't need to do any fancy factoring here. They just go away. So we're really left with just -5 and no h to plug in, right? We're left with this. That's just -5. I can't plug in h. Our final answer is -5. So that one is slightly simpler, I think, than some of the other ones that we'll see that will be quadratics. But again, you know, derivative is just glorified slope. It's the slope at an exact instant, and we call that in calculus the derivative, and it is marked as f prime of x. So the way that we can write this as a final answer is that f prime of x is -5, again, which we already knew from the start because of our knowledge about lines. Okay, guys, questions on the linear example there? Okay. Let's move on to a quadratic example. So I'm just going to erase a few pieces here. The quadratic example is going to be a little bit more in depth than the linear one. So let's say we have f of x, and this will be example 2. F of x is 3x squared. We'll do +5. Okay, so we did not do one that had, I think on Monday, we just did x squared like -3. It didn't have a coefficient in front, but it's not going to change anything. It's just going to make it a little bit more algebraically challenging, which is the goal. Okay, so same thing. So we want to have the limit to find f prime. We want to have the limit as h goes to 0 of, in our numerator, same thing, right? We want to plug in x plus h in for x to find the f of x plus h. So I'm just going to replace x with x plus h in parentheses first. So we're going to have 3x plus h quantity squared plus 5. So that's our f of x plus h. Then minus, in yellow, we'll do f of x. F of x is just your OG function, right? 3x squared plus 5. Okay, this is something that in calculus I say all the time, like to the AP kids, like calculus is not hard. The algebra is hard. That's what makes it difficult. So we've already done all the calculusing. Now on to the algebraing. So we need to square x plus h. That means multiply it by itself. We did this on Monday, but I'm just going to do it off to the side instead of in this like ginormous fraction that we have. So I'm going to take this piece right here, right? Because order of operations, PEMDAS, tells us that I don't deal with the 3 out front first. I deal with squaring it first, that exponent. So I'm going to do that off to the side over here. And we're going to square it. So I want you guys to practice foiling that out, right? Distributing it through. And you'll end up with 3 terms because 2 will be combined. Also, just has anybody talked to Jake Bartholomew or seen him in class? I feel lonely when no one talks.
I haven't seen
No, ma'am.
No,
I
no
haven't
one's
heard
seen him.
anything.
He wasn't in my last class.
Saw him yesterday.
Wasn't in it. Oh, who saw him yesterday?
Me. John.
Identify yourself, cadet. Who's talking to me?
John.
John, okay. You saw him what, on Zoom?
Yes, I did.
Okay. So he's alive and well.
Yes, he's good.
Okay.
He is today.
Okay. I'll reach out to him. All right, when we multiply this out, guys, we're going to get x squared plus xh plus hx plus h squared. These two are like because of the commutative property, so they're both xh's. X squared plus 2xh plus h squared. Okay. I just did that off to the side just to remind you that when we square this, it doesn't just become x squared plus h squared. You guys are good at that. I just wanted to make note. Okay, so we'll keep going here. So we have the limit as h goes to 0. We have the 3 out front, and then this turned into the x squared plus 2xh plus h squared. Of course, still the plus 5. And then I'm going to distribute the minus sign through. So we'll get minus 3x squared minus 5 all over h. When we distribute the 3 through, we're left with 3x squared plus 6xh plus 3h squared plus 5 minus 3x squared minus 5. That's a whole lot. But all the stuff that doesn't have h in it will cancel, hopefully. That means you did it right. If it doesn't cancel and you're left with something that doesn't have an h in it, you made an algebraic error. So the 3x squareds are opposites, they cancel. Plus 5 and minus 5 are opposites, they cancel too. I'm going to erase this up here, and we'll move up here to keep going. So we're going to have the limit as h goes to 0 of what's left, 6xh plus, oops, hang on, plus 3h squared all over h. Cool. All right, now even when we still direct substitute 0 in for h, we'll get 0 up top over 0 down below. That's still indeterminate form. So we need to factor. So in our numerator, we can factor out the GCF of h, actually 3h, and we'll be left with 2x plus h all over h when we factor. This h over h can now cancel. So now when we direct substitute 0 in, we're left with that 3, and we're left with a 2x. Then we don't need to write plus 0, right? I'm just putting a 0 in for this h, so it goes away. So our final answer is going to be 6x when we multiply. So, I'm running out of room here, but our final answer, f prime of x, is 6x. So I want to sketch something on the next slide just to show you what this means. You know, this is a parabola, 3x squared plus 5. So it's changing all the time. It's unlike a line. It's different. It's more complex. So I'm going to sketch the graph of that guy. 3x squared plus 5. The 3 out in front of the x squared just means it's skinny, skinnier than x squared. The plus 5 means it's shifted up 5 units on the y-axis. So when we sketch this, it's going to look like this. Something like that. So that is this function. And again, it's not a line. So if I were to sketch, you know, how we're changing at different points. So if I were to plug in like -1 or like 2 or something like that, right? Here's what we were told. We found that f prime of that function was 6x. So that means, how is our function changing at exactly -1? At exactly -1, we could figure out where we would be on the line if I plugged in -1. If we plugged in -1 here, we'd have 3 times 1, so 3 plus 5. So this is the coordinate point -1, 8 right here. That doesn't matter too much, but I'm going to draw how we're changing at that exact point. This is called the tangent line. And the way that that function is changing at exactly that point when x is -1 is a very steep negative change, right? Our parabola is going down and fast at that point when x is -1. How fast exactly is it going downwards? What is the slope of that tangent line? Well, we could plug in -1 off to the side here into our derivative. And if we plug in -1 into our derivative to see how we're changing at exactly when x is -1, when we plug in -1 here, we'll get 6 times -1. So this line right here, how our parabola is changing when x is -1 is visually, it's changing very quickly, very steep in a negative way. Algebraically, the slope of that tangent line that we drew, how we're changing is exactly -6 at that moment. So if we're graphing some sort of thing like how the housing market is changing over time, or the value of Zoom stock right now, you know, that's increasing rapidly. Let's say the value of Zoom stock before this whole coronavirus happened, it was going down, down, down. Then this is the change in March. It's going up, up, up really fast. So how something changes over time is how we can sort of capture what a derivative means. So anyway, this is called a tangent line. Tangent means touching at one point, exactly. So that goes with the derivative because it's how we're changing at an instant. If we look over at 2, I can't use 2 as an example, I made this too steep. Let's look over at +1. If we plug in +1 here, if we were to plug in +1 to our function, I would be at this coordinate point here, pretty close. So if we plugged in 1 to our function, I'd get the same output of 8, right? So I'd have the coordinate point 1, 8 again. How is our function changing there? Well, again, it's changing in a very, very positive way. Well, differently, it's changing in a positive way this time if we drew the tangent line. If we were to plug in 1 into our derivative, if I were to plug in 1, I get 6 times 1, 6. So our function is changing in a positive, steep, fast way when x is 1. So the parabola, depending on where we're at on the parabola, if we want to find out how we're changing at that instant, we use our derivative that we found and we plug in what instant we care about. So that's why this parabola is different from a line, because a line is always constant no matter what, and a parabola or something that's greater than a line is going to change in a different way depending on where we're at. Okay, I know that was a lot, but that is a main idea in calculus. And these lines here are called tangent lines. They touch at exactly one point and they show how we're changing at that instant. Okay, let's try another example with squareds. I'm going to have you guys practice this one on your own. So I want you to find f prime for f of x equals -2x squared plus 1. So if you have any questions, just shout them out while you're working. Use your limit definition of a derivative here. All right, I'm working through this one, just giving you guys some time. When we end up distributing the -2 through, that's where I'm at right now. Oops. Oops. There we go. I made an error and then I realized it when I didn't write down this -2 here when I copied down the f of x, and then I realized my error because they didn't cancel out. So that's how you can self-check. All right, once we're down to this point, it's just factoring. So when we factor out we can actually factor out, if you want to just factor out the h, that's fine. If you want to factor out 2h, that's fine. If you want to factor out -2h, that's fine. It doesn't really matter if you factor out the GCF or not. We're going to end up with the same answer. But you just need to factor out an h either way. So I'm going to factor out the GCF, which is -2h, based on what we have left here, which is this piece. When we factor out that -2h, we'll be left with 2x plus h. Now, if you factored out something different and didn't take out the negative, that's fine. You'll end up with the same answer anyway. Kind of a rule of thumb with factoring is that if everything's negative, it's easiest to take that negative out front. That way you're just left with positivity inside your parentheses. Then we can cancel the h's. So now we can successfully plug in 0 for h. We'll be left with a -2 out front and a 2x inside, which gives us -4x. So our f prime is -4x. How do we do? Thumbs up if that's what you got at the end. Yeah, okay, cool. All right, we're gonna do a slightly more challenging example to end with these algebraic examples today. So our last example will be f of x equals x squared plus 2x minus 3. And we want to again find f prime. Okay. So this one's a little bit more complex because we have 2 spots where x shows up. So we're going to have to plug in twice. So f prime is defined as the limit as h goes to 0 of f of x plus h minus f of x all over h. So we're going to plug in first f of x plus h. I'll do that in red. So I need to plug in x plus h not only to this x, but to this x also. So we're going to have x plus h quantity squared plus 2 parentheses x plus h and then minus 3. Then we'll subtract f of x in yellow. So x squared plus 2x minus 3 all over h. So I'm going to remember what happens when I square x plus h, right? We'll get x squared plus 2xh plus h squared. That was this piece right here. Then next I'm going to distribute the 2 through. And then a minus 3. Lastly, we're going to distribute the negative sign through. So we'll have minus x squared minus 2x plus 3. So be careful with your distribution. I will see if I did that all right, if everything cancels but the stuff with the h's in it. So the x squared should cancel. They do. I have opposites there. This next term won't cancel, neither will this one because they have h's in them. This one should cancel because it doesn't have an h. So positive 2x, negative 2x, good. Then this next term won't cancel. It has an h in it. But the minus 3 and the plus 3 do cancel. So we did that right. So we have the limit as h goes 0 of what remains, everything with h. Okay, if we plug in 0 for h by direct substitution, we'll get 0 over 0, which is an indeterminate form. That means our limit exists. We just have to do some algebraic factoring here. So in our numerator, we can factor out the GCF, which is h. We'll be left with 2x plus h plus 2 all over h. Again, the reason we do that is to eliminate the 0 over 0 issue, and it does. So those h's can now cancel since they are factors on their own. And then we can direct substitute and successfully h is 0. So when we do that, this term stays 2x. This goes away because it's 0, and we'll have a plus 2. So we'll have 2x plus 2 as our final answer. So f prime is 2x plus 2. Okay, the last thing that I want to look at to recap what we've gone over today is just sketching those tangent lines on a graph. So that'll be the last thing that we look at. So again, a tangent line is something we discussed earlier. The tangent line, the slope of the tangent line that we'll sketch represents the derivative. It's how we're changing at exactly that instant. And a tangent line, tangent means touch, and it's going to touch at exactly one point on our curve, and it's going to represent how we're changing at an instant. So if we have some function here, and I'll sketch the function in blue, and we'll call this f. And we'll pick a couple points on f. And if yours doesn't look exactly like mine, that's totally fine. You can kind of sketch really whatever function you want. If you want to just watch this part and then practice, that's cool too. So let's sketch the tangent lines at, we'll do one in red, x equals, we'll do at -1, actually -2, we'll do one at -1, and we'll do the last one at 3. So we'll sketch 3 tangent lines to see how our graph is changing at exactly those points. So tangent lines do not need to be long. They just need to be a short little line at that exact point, because we only care about at that instant, not really that far around the x value. So where is x -2? X is -2 here. And this would be the coordinate point on our function when x was -2. So that's the coordinate point, -2, comma, f of -2. How is our graph changing there? Well, the way that it's changing is a slight negative change. Just like that. We don't want to cross the function at all. We don't want to go through it. So I'm going to do something that would be wrong. I don't want to like cross through the function at all. But instead, I want to just touch it at one point to show how the graph is changing there. The graph is decreasing there at a kind of slow rate. So the slope of this tangent line here is kind of a small number, and it's negative. Maybe like -0.5 or something. Next, let's sketch the tangent line when x is -1. So x is -1 right here. So on our graph, this would be the point when x is -1 approximately, right? It's not perfect, I just sketched it. The y value is some negative number. But now, if you notice, our graph, our blue graph here is actually increasing here. So the tangent line is going to have a positive slope. It's going to be going up. It's going to look something like that. So even though these values are actually pretty close to each other, the way that our blue graph f is changing there is different. When x is -2, our graph was decreasing. The tangent line had a negative slope, it's going down. When x was -1, our graph was increasing there. Its tangent line had a positive slope. Lastly, let's graph the tangent line when x is 3. So here's approximately the coordinate point when x is 3, 1, 2, 3. And our graph is decreasing there very slowly. It almost looks linear here. It almost looks like a line. So our tangent line here looks something like that. That's how our function is changing when x is 3. So the slope of that function is not that steep, and it's also a negative number. So that's what sketching a tangent line means. And the slope of the tangent line is our derivative. It's how we're changing at that instant. Okay, guys. What questions do we have? We have any? Okay, your assignment is already sent out to you. I emailed it to you guys after class on Monday. It's going to be due tomorrow by 3:15 p.m. to the Dropbox on Blackboard. 4 problems look like these, something like this. 2 are linear and 2 are quadratic. Then the last problem, number 5, has you sketch a tangent line, which is what we did here. So it's having you sketch a tangent line at a particular value. So if you have any questions, I'll be on Zoom today and tomorrow at 2 o'clock. And again, if you have any missing assignments you need to turn in, please get those to me by Friday at noon. Coach Fogarty is going to send out an email to you guys with how to log into his stuff, which you will begin on Monday. If you are all good, you can peace out. And it's been a fun year, guys.
See you later, Ms. Damaj.
Bye.
Thank you so much.
Thanks so
Next
much.
year.
Bye, Ms. Damaj.
Bye.
Mr. Maj,
What's up?
do you watch Netflix?